All right, so we established in the last video that the spacing of energy between the three T2G orbitals and the two EG orbitals in an octahedral complex is given the nomenclature of delta O. Okay, so in this video, what we're going to talk about is what factors affect the magnitude of delta O. One is ion charge. So if you have as you increase metal ion charge on the same metal, that increases delta O. Why is this? Well, you have more charge, you're pulling in the electrons closer, that's increased metal ligand interaction. Remember, this is all about electron-electron repulsion, crystal field theory is. And so that's going to cause your delta O to go up. So for example, if you looked at hexaaqua manganese 2+, has a delta O of about 8,500 wave numbers. Compare that to hexaaqua manganese 3+, much higher at 21,000 wave numbers. Or you can look at hexaaqua chromium 2+, 13,900 wave numbers. When you go to the 3+ analog, it increases to 17,400 wave numbers. So that's a very straightforward trend that we can understand. Another very straightforward trend is moving down a family in the periodic table. So going from 3D transmission metals, the 4D transition metals, the 5D transition metals, or often called first, second, and third row transition metals, respectively. Moving down a family also increases delta O. Why is this? Well, you have the same amount of charge, but you have more protons, right? So that means you have increased nuclear charge. That's going to cause more repulsion, right? And you also have more steric room for ligands when they're at shorter metal ligand bonds. So when you have longer metal ligand bonds with these bigger orbitals, okay, going down on the periodic table, you're going to have more steric clashing. More steric clashing means more electron-electron repulsions, which by crystal field theory is bad. So if you look at this cobalt 3+ complex, you got 24,000 wave numbers for the magnitude of delta O. You go down one on the periodic table to rhodium, the analogous rhodium complex, and you got 35,000 wave numbers, and then you go down to iridium, one step down, the third row transition metal, now you've increased it further. So those are very straightforward trends. Increasing charge increases your delta O, increasing where you are on the periodic table, moving down a family also increases your delta O. Here's another trend. Of course, not just the metal matters, the ligands also matter. And this, they generally affect metals in the same way. So this series is called the Spectrochemical Series. So all metals with carbonyl ligands, CO ligands, will have relatively high delta O's. And all metals with iodide as a ligand will have relatively low delta O's. And if you look at this series, you can find lots of different versions of this series with lots of different ligands. It's hundreds and hundreds of different ligands people have explored and measured these on. It's kind of hard to see a clear trend. Yeah, the halides have this trend within themselves, but other trends don't really seem to make a whole lot of sense. And the reason why is because crystal field theory actually cannot rationalize this trend at all. Crystal field theory is a very simple model that just relies on electrostatics. Why would, for example, carbon monoxide have a stronger effect than iodide? If we're thinking about crystal field theory, more negatively charged ions should have a bigger delta O because you give rise to more electron-electron repulsion, right? That's what crystal field theory says is the origin of the delta O. It's all electron-electron repulsion. So you'd think that this should be sorted by charge, but it's not. You got neutral molecules kind of sprinkled in all over the place. So we need molecular orbital theory. The answer is it has to do with the specifics of all the different bondings that can happen with these different ligands, okay? And it's not just a simple electrostatic reality. There are additional bonding interactions between the orbitals that are on the ligands and the orbitals that are on the metals.